everybody, it's Mrs. Gano. Welcome to Chemistry in My Kitchen. We're going to be doing some stuff with water today and liquids in general. So if you look down here, I've got a kit of these magnetic water molecules here from a container, and we can see that they can connect and interconnect. We're going to look at just two of them here, first of all. So I have two waters, and if I put them next to each other, did you guys hear that click? When they come next to each other, and they're stuck to each other like that, okay? What happens if I try to put the white ends together? It's literally pushing away. What about the red ends together? Also, it's literally pushing away. Okay, I can't get them to stick. The only way I can get them to stick is like this, all right? So we know that these are forces between the water molecules that cause them to stick together and to be attracted to each other. And so we're going to be talking a little bit about that. These are the intermolecular forces that water experiences, okay? So if you look at a whole random assortment of liquid water, we can see that there's really a million different ways that these water molecules can connect to each other, and lots of different structures and things that they can form. And the water molecules have kinetic energy, and so they're all moving. And these little intermolecular forces are easily broken and reformed. Okay. Now here's a salt crystal. So this is a large salt crystal made of sodium and chloride ions. And we know that when salt goes into water, it dissolves. And so what is it that water does that breaks it apart? So here's just one little piece of a salt crystal. So I'm just going to take one of the ions, and I'm going to put it with some water molecules. Sorry, hiding it from... And so you can see there's a strong attraction here in only a specific direction for this ion. And this ion is now surrounded by water molecules. It's solvated or dissolved. All right, now this ion, I can do the same thing, but nothing happens in this direction. But there, that's where the attraction is for this ion. We can see that. And so this ion becomes surrounded by water molecules, and it again is solvated. And that's when this crystal goes into a large amount of water, that's what happens to every single ion. They individually get pulled off, surrounded by water, and dissolved in the water. Okay? Now, I have another molecule here. This is called ethane. The gray ones are carbon. Let's see if I can write this sideways here. C2H6. That's ethane. What happens when I surround ethane with some water molecules? So I'll get some more water molecules out. Nothing happens. I can't get water to interact with ethane. The water molecules are interacting with each other, but I can't get the water to do anything with ethane. So what does that tell us about ethane? Obviously, we know water is polar, and if ethane is not interacting with water in any way whatsoever, ethane must not be polar. It must be nonpolar, right? Now my ionic compound interacts super well with water. It's not polar, it's ionic, charged particles. Ethane must have no charged particles and no charged ends either, because it doesn't interact at all with water. This is our like dissolves like rule when we talk about things interacting with each other. Okay. The other thing I want to show you guys is ice. So over here, I have the structure of ice. This is now solid. So the particles have no kinetic energy. They're not moving. And they've set up this arrangement so that they can have as many interactions as possible between the molecules. So these are our intermolecular forces that we're talking about. And we know that water sticks together with these intermolecular forces. And the strongest one is hydrogen bonding. And so ice has this very, very open structure here. It's actually much less dense than liquid water. If I look at liquid water where the particles can move, look how much closer they get to each other. And they're all moving past each other with some kinetic energy. But ice, when it loses its kinetic energy, it sets itself up in a way that maximizes the hydrogen bonding between the molecules. And so that's why ice floats on water. Because of the low density, because of the maximization of the intermolecular forces. All right, Now, if I want to take ice and melt it, what do I have to do? I have to add kinetic energy to these particles, and I have to separate them from each other. I am overcoming intermolecular forces. So I'm separating the water molecules from each other, overcoming intermolecular forces, and some of them reform as they gain more kinetic energy. But am I breaking the bonds in H2O? Am I actually separating this hydrogen from this oxygen here? Of course not. I'm not going to break any covalent bonds. This would take much, much more energy. So all I'm doing is overcoming intermolecular forces to separate them. Same thing if I want to separate a liquid. I'm going to overcome the intermolecular forces and allow these particles to vaporize. Okay? But again, in every case, in the ice form, in the liquid form, in the vapor form, the water is still the same. It's still H2O. All right, so now we've looked at water a lot. Let's look at liquids in general. Okay, liquids are particles that flow past each other, but the intermolecular forces between them keep them closer than gases. But they are less dense than a solid. What are the intermolecular forces? Again, there's three kinds: London dispersion forces, dipole-dipole attractions, hydrogen bond attractions. Okay. One important thing about a liquid is that they all have something called vapor pressure. The vapor pressure is the force caused by vapor particles above a liquid. It's affected only by the temperature and what type of liquid it is. So if I have a liquid in a container, some of the particles on the surface have enough kinetic energy to escape. They bang around and hit the walls of the container and cause a pressure that's called the vapor pressure. The process of boiling occurs as I heat a liquid. The vapor pressure steadily increases. More and more particles have enough kinetic energy to escape. Once the vapor pressure, and you can see here, once the vapor pressure equals the air pressure that's pushing down on it, then bubbles of vapor can actually form within the liquid. And that's what happens when something boils. So when you boil a pot of water, those aren't air bubbles that are coming out. Those are bubbles of water vapor that are actually coming out. And it's because you've added so much kinetic energy that the water has a high enough vapor pressure to overcome the air pressure, and vapor can form. Okay, so this is general about liquids. Let's look at a couple other properties of liquids. Viscosity is a property. It's about the resistance of a liquid to flow. Things that are viscous would be things like honey or ketchup or molasses. Water is actually not considered very viscous. It flows really well. And it's because the molecules of water are really small and they don't tangle up very well in each other. So things that are viscous tend to have larger particle size and get tangled. Surface tension is another property of liquids. It's a measure of the inward pull by particles in the interior of a liquid. Water has an incredibly high surface tension because the water molecules are super attracted to each other. Surface tension is what allows water bugs to walk across water, and it's what causes water to form droplets because the particles inside the droplet are so attracted to each other. Capillary action is another cool property. That's the movement of liquids up a very thin tube. And it's caused by two things: cohesion, which is the particles sticking to each other, and adhesion, which is the particles sticking to the walls. This is what causes water to rise up plants, the stalks of plants. It's either the xylem or the phloem or something like that the water is attracted to, and very thin tubes allows water to move up. Water has a super high capacity for capillary action, again, because of the very strong intermolecular forces between particles. Finally, we already talked about vapor pressure. Water has a very low vapor pressure. Why? The particles are super attracted to each other, and so they tend to not vaporize. Because there's such strong intermolecular forces in the liquid, it's very hard to get them to vaporize. Because of that, water also has an incredibly high boiling point. The lower the vapor pressure, the higher the boiling point of a liquid. You have to put more energy in to separate the particles from each other. As a matter of fact, water also has a really, really high heat of fusion, which is a melting point. It's very hard to separate molecules from each other in the ice or the solid phase because of all the intermolecular forces that are there. Finally, water has a really, really high heat capacity, which we talked about in our thermo unit, and it's very hard to cause the particles to move and give them kinetic energy and raise their temperature compared to a lot of other substances. Okay, so that's a quick summary of liquids and water, and I hope you guys have a great day, and we will talk to you soon.